Okay, let's see if we can apply some of what we've learned about tolerancing. In the sketch at right, the designer has provided the dimensions required to define the nominal sizes, the diameter, and the length of this cylinder, and also a plus or minus tolerance. If we analyze this sketch a little bit, we can see that if we apply a tolerance to the part's nominal dimensions, that the diameter of the cylinder could range anywhere between 0.97, which would be our nominal size of 0.98 minus 0.01, that's 0.97, to a maximum of 0.99 in diameter, which would be 0.98, the nominal size again, plus 0.01. So the diameter of this cylinder can range in size between 0.97 and 0.99, and it should still pass inspection for that feature. The length of the cylinder, which is 2.00 plus or minus 0.01, if we subtract 0.01, we will come up with a minimum length of 1.99, and if we add 0.01, we'll come up with a maximum length of 2.01. When the cylinder is at its largest diameter, which is the 0.99, a designer might say that the feature is at maximum material condition, which sometimes they just shorten to say MMC. When the cylinder is at its smallest diameter, which would be 0.97, we say that the feature is at least material condition. The length of the cylinder is at maximum material condition when the length is at 2.01, and at least material condition when it's at 1.99. So remember that the maximum material condition is the condition of a feature when it contains the greatest amount of material. That's why when the cylinder is its largest diameter, it's at MMC, and when it's longest, it's at MMC. Least material condition is when a feature contains the least amount of material. So when the diameter is at its smallest, which is 0.97, and it's at its shortest, which is 1.99, we would say those two features are at their least material condition. All right. Now, in the design sketch here, we have a block that has a hole drilled through it, and that hole has a diameter of 1 plus or minus 0.01, and then the location of the center of that hole from this edge down here is 1 plus or minus 0.01, and from this edge over here, it's 1 plus or minus 0.01. So the hole is actually located from two datum features, the bottom edge of this part and this side edge over here of the part. A datum feature is an element like an edge, a plane, an axis, a point, a hole, or a surface, or other feature that serves as a reference for defining the geometry of an object. That should say of and, not and. The designer has noted a tolerance on these of plus or minus 0.01, and plus or minus 0.01, and plus or minus 0.01 up here. And remember that a machinist may look at plus or minus 0.01, and they may add another 0, and instead of saying 0.01, they may call that 10 thou. So let's calculate the maximum material condition for the hole. So this hole has a nominal size of 1.00, and if we take the minus tolerance and we subtract that, our hole's diameter would be 0.99. If we add to the hole's diameter, the diameter would be 1.01. Which of those is maximum material condition? Well, you might guess that it's 1.01 because the number's larger, but you would be incorrect. When the hole is the smallest, the hole is at MMC, maximum material condition, because the part actually has more mass when the hole is smaller. In other words, you could say that the part weighs more when the hole is smaller than when it's larger. So what's the least material condition for the hole? Well, if you cut a larger hole, so if we make it 1.01, that would make this feature at least material condition. So I want to point out the difference between a datum feature and a datum. A datum feature is like a surface or an edge that we're dimensioning from, or that we're referencing a dimension from. But In the real world of geometric dimensioning and tolerancing, a datum is a theoretically ideal or perfect line, point, axis, or surface that tolerance is a reference from. So here's the thing, because this is a manufactured part, measuring from one of the sides is not really measuring from an ideal surface or plane. But if you took this same object and you set it on a granite surface plate, and a surface plate is a piece of granite that has a very smooth surface on it. If you set this part on a granite plate and you measured from the top of the granite plate to the center of the circle, that would, or the center of the hole, that would be what we would call measuring from a true datum. So often the datum lies offside, lies off of the part, and the datum is usually more perfect than a part surface itself. And sometimes we use a machine to measure parts called a coordinate measuring machine. Sorry, I've been at this too long today, which is referred to as a CMM. And a lot of times the CMM actually creates a virtual datum. That is, it does a digital version of a datum. And so it determines that what if there was a perfect plane butted up against the edge of your part and you measured from that, then how far over is the location of like the center of this circle, for example. Now, when we look at this part, I want to point out something about these dimensions that locate the center of the part. The closest that this part right here could be to this edge, if we applied tolerance to our nominal size right here, the closest at the center of this hole should ever be is at 0.99, and the farthest from this edge would be 101. If it were a true position, it would be right at 1.00, but we know it can move back and forth along between this 0.99 and this 101, and it would still pass inspection. The same is true if we dimension from this bottom edge. The nearest that the center of this hole can be to this edge down here is 0.99, and the farthest the center of this hole can be from this edge is 101. So when we look at this tolerance zone right here, we see that it's actually square, and it's 0.02 wide. It's 0.02 in this direction, and it's 0.02 in the vertical direction. So what we have here is a square tolerance zone that measures 0.02 by 0.02. Now, the center of our hole can land anywhere inside that square tolerance zone, even out here at the four corners of that tolerance zone. And believe it or not, that square tolerance zone can cause problems in making parts that align with each other. But still, when the part is inspected, the inspector's measurements will be made from the same datum edges that are defined in the technical drawing. So when this is inspected, the person making the inspection won't dimension from this side over. They'll dimension from this side over, and they'll dimension from this side up, rather from this edge down. So we want to dimension our part using the same datum features that our designer did, because that's the way that even the part will be inspected. As I said, a square tolerance zone is often considered a shortcoming of this type of dimensioning that we're doing here, which is called coordinate dimensioning. And so there is another type of dimensioning and tolerancing called geometric dimensioning and tolerancing that expands on what we're talking about today. And GD&T sometimes allows designers and manufacturers to avoid the problems that come up with a square tolerance zone. So let's calculate a fit between these two parts and see how well this part would fit into that hole right there. All right, so first off, let's look at this hole. Let's say they make the hole at 1.01. So this would be the widest hole it could be. And let's say they make the cylinder at 0.97, which would be the smallest it could ever be. Well, that would certainly fit through very easily. And if we took the difference between this wider hole and the smaller cylinder, what we'd find out is that what we would have is the best case scenario for assembly, and we would actually have a clearance of 0.04 inches. Because if this were 101 and this were 0.97 and we subtracted 0.97 from 101, we would have 0.04 inches or 40 thou. That's how much clearance we would have. But what happens if the hole is made at its smallest size, which we said is its MMC, and what if the cylinder is made at its larger size, which is its MMC? That would set up what we call the worst case scenario for assembly, because it's more difficult to assemble those parts when the clearance is less. So if this is 0.99 right here, and this diameter right here is 0.99, it would be difficult to fit that cylinder through that hole. Not impossible, because there's no interference because they're the same diameter, but you would have to be very careful, and you'd have to line this cylinder up exactly with the center axis of this hole. So if this hole were drilled off at a little bit of an angle and you tried to put this through, you couldn't push that straight through. This cylinder would also have to go off at a little bit of an angle in order to fit through there. So if they're both at 0.99, the fit would be tight and it would be difficult to assemble them, but not impossible. So what if the designer realized that when this is at 0.99 and this is at 0.99, it's going to be difficult to assemble those two? How might they fix that? Well, one thing they could do, they could change this number here and maybe make that 0.97 instead of 0.98. If this were 0.97, then the largest the cylinder would ever be would be 0.98, because if you start at 0.97 and you add 0.01 to that, then the largest this would ever be is 0.98 if we start at 0.97 instead of 0.98. So if this were at 0.98 and this hole over here were at 0.99, we would be assured of having at least 1/100th of an inch of clearance between those two. All right. Or we could go the other way. We could keep this where it is. And so let's say it's at 0.98. So the largest the cylinder could ever be is 0.99. All right. So let's say this is at 0.99. The designer might come up here, instead of saying that this hole's nominal size is 1.00, they might make the nominal size 1.01. And that way, when we subtract the 0.01 tolerance from it, it would go from 101 down to 1.00, which would be 1/100th of an inch larger than the cylinder if it were 0.99. So I hope that makes sense. So we call that distance there, or the clearance that we have in here, the allowance. And so the minimum clearance or the maximum interference between mating parts is referred to as an allowance. Now, it might even be desirable to have an interference between this cylinder and this hole, so that we have to press this through. And by pressing it through, what it might do is it might jam this in there, and it might be a way of attaching this cylinder to a part without welding it or molding it like that. And so sometimes we want an interference fit, and sometimes we want a very loose fit, and sometimes we want a fit that's just a sliding fit that will allow it to clear but slide through pretty easy but not have a big clearance in it. Now I'm going to back up one. I want to go back to this one. I think what we said here was that when this cylinder is made at its smallest, it's at 0.97. And when this hole is at its largest, it's at 1.01, and that gives us a 0.04 clearance. Now, we refer to that as the best case scenario because it's very easy to assemble those two parts when this is small and that's large right there. But it's possible that the designer is going to look at that and say, that's too much clearance, because what could happen there is that cylinder might rattle around in the hole, or it might, vibrate out of the hole, or whatever it is. And so that's another reason why, even though we say this is the best case scenario, it really may not be the best. That's kind of a relative term that we use. And even the worst case scenario might actually be a good thing if we want this to fit very snugly through there, right? So it's all relative, and it just depends on what the designer really wants. So remember, we call that clearance or interference allowance. All right, so how do we confirm tolerances of manufactured parts? After the part's manufactured, we have to confirm it, that it was manufactured within the size limits of the dimensions and tolerances noted on the drawing. So this step in the manufacturing cycle may be performed by a quality control inspector using precision measuring equipment, which we call metrology equipment. And what they will do is they will measure the features of the part to find out what the actual size of the part is. Parts that measure within the allowable size limits, so parts that fall within the limits of the tolerance, will pass the quality control inspection, while parts that measure outside the limits are rejected. So if the parts are made outside of the limits, then you don't have to purchase those parts from the manufacturer. But if they're made within the limits, you do. So the actual size refers to the measured size or location of a feature of a manufactured part. So after the part is manufactured, the quality control people, wherever they are, they will measure each feature and they will compare that against the tolerances and the dimensions on the drawing, and they determine whether or not that part passes the quality control inspection. Now, I have a question for you. Do designers and manufacturers like tolerances? Is this true or false? So it says designers and manufacturers like tolerances, true or false? Well, the answer is true. They both like tolerances. And the reason for that is this. If you've clearly defined the size of your parts when you're a designer and you send those to the manufacturer, you can avoid problems and disputes later. And putting tolerances on parts helps to clearly define the expectation for the sizes and orientation and location of features. So it's a good thing to have things like tolerances on a part. When the features of a part are manufactured within the dimensions and tolerances that you put on your engineering drawing, if you're an engineer or designer, then you're going to like that the parts are made within that, because then you can be sure that the design intent that you had in mind, like how the part fits, forms, or functions, you can be sure that your design intent has been maintained and the parts are going to fit, form, and function like you wanted them to. All right. So this is another good reason why designers like tolerances. When the parts are manufactured within the dimensions and tolerance that were sent to the manufacturer, the organization that ordered the parts is obligated to buy the parts. So this is why manufacturers like it. They know that if they manufacture the parts within the tolerances and within the dimensions, that the person who ordered, or the organization that ordered the parts, is obligated to buy them. So a lot of times they can put this into a contract, and they will say that if we manufacture these parts within the specifications and dimensions and tolerances specified on the drawings that you're going to provide to us, then you will have to buy those parts as long as we stay within those tolerances. All right. And so this protects the manufacturer, and it also protects the designer, because the designer knows if these parts are made within the specifications, they should all fit together or function the way they intended them to. So tolerances actually are a good thing. So, because this is a video, I can't take any questions right now, but I hope this helps clear up a little bit about how you might apply some of the things we've been learning about tolerance.